Hello, everyone. We are on section 3.5 from chapter 3 in statistical methods for rates and proportions. In this section, we're talking about simple confidence intervals for the difference between two independent proportions. So we're going to go back to the example that we've been working on where we have characteristic A and characteristic B. We have 150 people who have characteristic A and 50 people who do not. We're going to reorder the factor so that present shows up first and absent shows up second. That way our table looks like what we've seen in the book so that we're more comfortable with it. All right, we're going to do NI dot and N dot J. Remember, NI dot are the row sums and N dot J's are the column sums. Just to double check we've done that correctly, we're going to look at NI dot and look at N dot J. We see 150 and 50, 25 and 175. So our NI dots and N dot J's look correct. We can change this over to the proportions by taking the 1 element of our table and dividing it by the first row sum that we saw, NI dot square bracket 1. And then we can look at the 2 element of T and divide that by NI dot and the second one of those, and that will give us P1 and P2. When we run that through, we see that P1 is 0.1 and P2 is 0.2. We can calculate Q1 and Q2 in the regular way by doing 1 minus P1 and 1 minus P2 respectively. And then we can set N1 dot as the first element and N2 dot as the second element. All right, in our book, it gives us a formula of standard error. That's equation 3.13. And if we look at the standard error for the difference in the proportions, we get the square root of P1 Q1 over N1 dot plus P2 Q2 over N2 dot. So we can get the standard error. And then we can set our alpha level of 0.05. And when we want to give R the alpha level or the area under the curve, we can ask it, what is the Z value associated with that area? And since we're going to be doing a confidence interval, we're going to have alpha over 2 in each tail. Setting lower dot tail equals to false says, I'm giving you the area in the upper tail. So if you wanted to get an equivalent value of Z crit and you decided to put in Q norm and you did 1 minus alpha, so you told it or 1 minus alpha over 2, so you put in 0.975, lower tail equals true, it should give you the same thing, okay? But I'm going to use this trick to say it's the upper tail because that's how our book has defined it. But just to show you, 1 minus alpha over 2. The default is lower tail equals true. Okay, by doing that, we should still get 1.96. So it doesn't matter, it's your preference. But remember the difference between Q norm and P norm. In P norm, you're giving it a Z value and it will tell you the area. Whereas in Q norm, you're giving it the area under the curve and it's telling you the test statistic that's associated with that, or the critical value in this case, since we gave it an alpha level. All right, we can calculate the continuity correction, and I've just called this cont.core, and that's given in our book as well. And I can do the difference of proportions, it's just P2 minus P1. And we use the regular formula. We take the difference of proportions, subtract the critical value, multiplied by the standard error, and subtract off the continuity correction. Or we take the point estimate, which is our difference of proportions, add the critical value times the standard error, plus the continuity correction. I'm giving the column names of CI, lower and upper, because that's telling me my bounds of my confidence interval. And here I get the confidence interval, negative 0.034 up to 0.235. And that's the same that's given in the book as well. If I wanted to, I could round this to 4 decimal places just so that it looks prettier for the output. And really, in all of this, I could just use the built-in function called prop.test, and it will do everything for me that I just hand coded. Prop.test, if I tell it the X values and the N values. So our successes are in T11 and T21. And then the row marginals N1 dot and N2 dot tells us our totals, and we have a 2-sided test. And by running this, you'll see here that I get the same exact confidence interval, right? Because it's giving us our 2-sample test for the equality of proportions with the continuity correction. And since we said it was 2-sided, then it gives us our 2-sided confidence interval, gives us the estimates of the proportions. And just like before, you could give this a name. Let's say test gets this prop test. And I could say names of test. And if I do so, I know what I can pick off. Statistic, parameter, p-value, estimate, and so on. But if I just wanted the confidence interval on its own, I could say test $ confidence.interval. And when I do that, I get the negative 0.234 up to 0.034. All right, if you notice, these are reversed comparatively, right? They're very similar, but it's reversed. And that's because of the way that I put it in prop test. If you want to get exactly what the book got, let's just rename that test and let's switch these T21s and T11s. Okay, if I switch this, right, that will tell R the way that you want them subtracted. And I can pick off the confidence interval again. And now we got exactly what we thought we would get of the negative 0.034 and the 0.234. At the end of the day, does it matter if you subtract P2 versus P2 minus P1 versus P1 minus P2? Not really, except for you may want to talk about the difference in a particular way that helps people understand what you're doing. So that will determine which order that you would like the confidence interval to be showed at. But what's more important is that you interpret correctly the direction of the subtraction that you did. All right, I hope you learned something in this video, and I'll see you guys next time.